So let's talk a little bit about exponential growth and decay in a calculus sense, because you may have seen all this in an algebra class, but it's quite different in calculus. You will need what you needed in algebra, though. All right, so take a quick moment to read this paragraph that I got from the book. It actually explains everything very well, and then come back after you've paused the video for a minute. So the most important part of this is where they talk about how a function is equal to a constant of it times its derivative. So essentially what you have is y prime is some constant times the function itself. So there are functions that we've seen that do this. For example, if you have something like y equals like 5e to the 3t, the derivative of this is, all right, so let's talk about this. E to the u, whenever we take the derivative, this is u prime e to the u. All right, so we go 5 times 3e to the 3t, which I can write as 3 times 5e to the 3t. Still y prime. So y prime is equal to, now, 5e to the 3t is y. So I can replace this piece here with just y, and I get 3 times y. In other words, y prime is 3y. So it goes according to what we said up here, or right here if you want, that a function's derivative is equal to a constant times the function itself. So let's just play around with this just a little more and see what there's a pattern. So let's start with like y equals, let's say 2e to the negative 6t. So let's take the derivative. This is 2 times negative 6e to the negative 6t. Now I'm going to rearrange the constants here. So this is negative 6 times 2e to the negative 6t. All right, so 2e to the negative 6t is sitting right here and here. So I can replace this piece here with just y, and I get y prime equals negative 6 times y. So once again, we get what we had up here, which was y prime equals a constant times the original function. So let's see if we can write this down in general. So what we had was, let me erase some of this. We had y equals a constant times e to another constant times t. We took the derivative with respect to t, that's a constant, times k e to the kt. Switch the constants, k times c e to the kt, and then we replace this c e to the kt with y, because that's what it started out to be. So this is just y prime equals k times y. Exactly what we talked about right here. So it would make sense that c e to the kt is a really nice function that we can work with this. And so this is why it's called exponential growth and decay, because there is an exponential function involved with this. It basically solves the problem of what they talked about in this paragraph. It is a good model for, it's a good model for when we have a function rate of growth that's possibly related directly by a constant to the original function itself. All right, so you can see in here in all this that there are some great applications of this. All right, so what I want to point out though is a couple of things. First of all, if you plug in 0 into this function here, so let's talk about this function here. If you plug in 0, so y of 0, so this is y of t, right? It's y of t. Y of 0 is c e to the 0 times t, or e to the 0, or it's actually just c times 1, because e to the 0 is 1. So y of 0 is this constant c. So we're going to call this the initial value, so initial amount or value of the substance or population or whatever y represents. Substance, population, material, whatever it is, it's the initial amount. So if they give you an initial amount, that tells you that you should plug in C for that initial amount in for C. Now, one thing I want to point out before we go to an actual example are a couple of things. If you notice on the problems that we did, the exponent was, let me break this bigger. The exponent here was positive and the exponent here was negative. Yeah, so positive and negative. So if the k, so remember we called that k in the what we did over there in general. So if k is greater than 0, this is called exponential growth. And if k is less than 0, this is called exponential decay. All right, so let's do this example right here. So give yourself a second to read it. So what I want to point out here is that it says a bacteria culture grows with a constant relative growth rate. So what does that really mean? Let's look at that for just a second. So what we had was y equals k, y prime equals k times y. Now if you take y and you divide by it on both sides, this is k. And so the left-hand side of this is called the relative growth rate because it is the growth rate relative to the actual population size. So it's the growth rate divided by the population. And if you notice, that is a constant, right? Because you have y prime over y equals a constant. So another way to say that a function is like proportional to the derivative is proportional to the population is to say that it has a constant relative growth rate. All right, so we can use all the mathematics that we derived. So let's see what we've got here. The bacteria count was 400 after 2 hours and 25,600 after 6 hours. So since it's a constant relative growth rate, we can say that y prime equals k times t. I'm sorry, k c. Well, it's k times y, and then y is equal to a constant times e to the kt. That was all the work we did before. So using what we have up here, the bacteria count was 400 after 2 hours and 25,600 after 6 hours. We can plug those two values in. So 400 after 2 hours, so 400 equals c e to the k times 2, so 2k, 2 times k, and then it said it was 25,600 after 6 hours, so 25,600 after 6 hours. Move all this out of the way. So this is 6 times k. All right. It says, well, what is the relative growth rate? And express your answer as a percentage. So the relative growth rate is k. So we need to find k. So let's work these two problems. We have these two equations. We have this one here, and we have this one here. And we have two unknowns. So we can solve for c and k. So what I'll do is I'll take this one and I'll solve for c. So c is 400 over e to the negative 2k, sorry. And also that would be 400 e to the negative 2k. And now I'll plug that in for C here. So that's 25600 equals 400 e to the negative 2k, e to the 6k. So we get, if you divide both sides by 400, you get 64 on the right, and on the left, and on the right, you get e to the 4k power. So then you take the natural log of both sides, because whenever you have a exponent as the variable you're trying to solve for, I'm sorry, if the variable is in the exponent, then you need to use natural log or log to solve. If it were something like 2 to the 4k, you would use log instead. But since it's e, natural log is much easier. All right, so if you have a question about that, email me, all right? I don't have a problem explaining it to you in further detail. So now this is natural log of 64. 4k comes down in front using the power rule. Natural log of e is equal to 1. And so k is the natural log of 64 over 4, which there's a couple ways you can go from here. You can make this natural log of 4 to the third over 4, and then make this 3/4 natural log of 4, or you can just go ahead and find out what that is, and it's 1.03972 about. All right, it's about that. All right, so there's a couple ways. Okay, so once you have k, so this is k. All right, now we can go back up to what c was, and we can plug it in. So we get c equals 400 e to the negative 2 times, and then let's make this 3 over 4 natural log of 4. I'm keeping it like that because I want to get a precise answer for it. So we get 400 e, and then multiplying that negative 2 through, we get negative 3 over 2 natural log of 4 right there. All right. And so you can make C approximate. Well, actually, it's 50 right out. So if you don't approximate it here, then this answer is more precise, and so is your function. So your function, well, that's part of the function. So if we go back up, the function was C e to the kt. It was here. So we're going to plug in both of these values and get what we need. So I'm going to take that down here. I'm going to get y equals 50 e to the kt. So you can write it as 1.03972 t. Now the book has the following answer. It has y equals 50 times 1.2, I'm sorry, it says 2 to the 1.5 t power. And how they get from here to here is a lot of work. So it's not a problem to do it that way. It's just, I don't think it's worth it, because the math to get there is so full of pitfalls that if you have an approximation here, see, this is an exact answer. This approximation is good enough for me. So let's go back up to the problem and see what we need. So this is the actual, well, the actual function is what either one works. All right. Okay, so we found what's the relative growth rate as a percentage. K is the relative growth rate, and that is about 104%. It's a rate. So remember that K was the relative growth rate. That's what we went through up here. So since it's a rate, that it says, yeah, it's a percentage, so 104%. It's not a percentage because it's a rate. The relative growth rate is 1.03972. All right. What is the initial size of the culture? The initial size is C, and we found that to be 50. Find an expression for the number of bacteria per hour. We did that right here or here. That's that. And then find the number of cells after 4.5 hours. Let's plug it into both of these and see what happens. So we're going to plug in t equals 4.5 into both. So if this one gives you, and then this one gives you. So I did these on the calculator, and they're virtually identical. So it's really not worth going through all the math to get to this equation right here. And to be honest, and so we get 53.82. All right, cells. And now, what's the last thing we need here? It's probably just going to be some algebra. Find the rate of growth after 4.5 hours. So we're going to use this here, where we have the rate of growth is right up here. And so all we need to do is plug that in. So we have dy over dt is equal to, or y prime. Let's just write it about y prime. So it's y prime over y was k. And so y prime is k times y. So we'll plug in y prime equals k was 1.03972 times the 5382. And we get 5585.8. So 5586 cells per hour. So it's per hour. That if you ever are concerned about what the units are for a derivative, remember it's just what's y prime is dy over dt. So y is a number of cells and t is in hours, and so it's just cells per hour. Okay, and then when will the population reach 50,000? You just plug that into this right here. Plug it in 50,000 equals 50 e to the 1.03972 Now, the way you do this from algebra is you divide through by 50 and you get 1,000. And you have e to this power. And then you take the natural log of both sides. When you take the natural log of the right, it'll be 1.03972t natural log of e, because this will come down in front of the natural log. Natural log of e, this is equal to 1. And so you get t equals natural log of 1,000 divided by this number 1.03972. And you get 6.64 hours. And there you have it. So that's that problem.